So I started the recording. The floor is yours.
Okay. Well, thank you very much, Patrick, for giving me the opportunity to be here. As Patrick's mentioning, yesterday is Independence Day here in Mexico, so we are celebrating. So I'm very happy to be here. I have seen some of the talks that are on YouTube, and they are fantastic. So I'm really happy and honored to be here. Thank you very much. So I'll talk about these things are called intersection patterns and Tverberg type theorems. So let me begin by mention that, this is a joint work with several people. Some parts of the things that I'm going to talk about are with some people, some with other, but in general, this is more or less the team. So Jesus de Loera, who already have given a talk in this seminar, is a participant on this work. Tommy Hogan, who's a student of Jesus, a PhD student, well, he graduated already. Edgar Jaramillo, who is current student of Jesus. Antonio de Jesus is a student of mine, a PhD student in Mexico here in Querétaro. And Dominic Young is not part of the team anymore. He was an undergrad in Davis, and now he left, and I don't have contact with him anymore, but he participated in this group, of course. So I decided to divide the talk in several parts. So in the first part, I'll give some basic definition, and then I want you to explain a little bit what Tverberg theorem says. In the second part, I will talk about purely combinatorial way of seeing is a relation between some graphs and words. And the third part is the idea of putting things together, like Tverberg together with graphs and words that apparently at the beginning seems to have nothing to do with each other. And at the end, I'll just gonna mention a little bit of these things that we are doing later, and what are interesting possibilities and possible applications. Okay, so let me start with a little bit of motivation. So imagine that I'm a bird watcher, and I know that around my town, there are some possible type of birds. So here I just place 4 type of birds that are around my town. And imagine that since I'm an avid bird watcher, every time I go outside my place, I record the date and the time I see certain bird. So say on Monday at 7 o'clock, I see the matraca, and then at the following day at 8 o'clock, say I see the bolsonero, etc. And I continue record what's going on and what are the birds that I see on my backyard. And imagine that I'm interested in knowing what type of interactions are between these birds. All right? Okay, so, okay. Oh. Okay, so I'll talk about nerves. So what's a nerve? Interesting, it doesn't let me share if I don't put okay, there you go, sorry. So let me tell you what a nerve is, okay? So a nerve is gonna be the following. It's a way of codifying the interaction or the intersection of the family of convex sets. So imagine that I give you a family of convex sets, and I'm gonna define a complex in the following way. So let's start with this family of convex sets. and I'll put a vertex for each one of my convex sets. So I have a vertex 1, 2, 3, and 4, which represents each one of these convex sets. If the set 1 and the set 3 have a point in common, then I'm going to draw an edge. Similarly, 1 and 2 intersect, 2 and 4 intersect, 4 and 1 intersect. So I have each an edge for each one of these pairs. But also notice that these 1, 2, and 4 have a point in common right somewhere here. Therefore, I'm going to draw a triangle that it's telling us that these 3 convex sets have a point in common. In this other example here, I have another 4 convex sets, but notice here that the 4 of them have a point in common. Therefore, I'm going to have a simplex in this case that is a tetrahedron, but it's completely full. Okay. And this is telling us that the 4 elements on my family of convex sets have a point in common. Okay, so that's the nerve of a family of convex sets. Okay, I can do that in another way, but instead of having convex sets, imagine I have a set of points. And I decide to partition these points in color classes. So I have a red class, a blue class, and a green class. Then I want to define what the nerve of this partition is. And the only thing I'm going to do is I'm just going to extend the definition I just gave you before. So I'm going to take the convex hull of the red class, the convex hull of the blue class, and the convex hull of the green class. And then I'm going to take off nerve of that family of convex sets. So in this case, I have a point that is in common of these 3 color classes. Therefore, I have a 2 simplex in this case. Okay, so that's a nerve of a partition. Okay. So observe that if I change my coloration or my partition, that it right away gives me different nerves, right? So this is the nerve I started with. But of course, if I change my partition and instead of that being, this one I colored green instead of blue, then this gives me a triangle, like in this case, this red and this blue. So if I take the nerve of that, now instead of being a simplex, this just gives me a path of length 2, okay? So once again, this nerve is just a way of codifying what's the intersection pattern of my family of color classes of points. Okay, here, this is just another example that shows that I can get different and weird kind of nerves, okay? So going back to my motivation, so assume I have my M type of birds on my type, and I'm interested in understanding what's the interaction between these birds. So if I see my matraca on Monday, and then on Thursday I saw it again, and some way in between on Wednesday I saw it again, it's not too crazy to assume that the matraca was on my town all the time. So taking the convex hull of these blue points is not that crazy in terms of applications, let's put it like that way. So if I have a situation like this, then of course all the birds are on my town at the same time. So the nerve of this in this particular case will be again a simplex, in this case, a tetrahedron again, full once again. So I hope I'm being clear so far. All right, so this is another possibility. Say I have a bunch of bacteria on certain part, and then again, I'm taking the intersection of the convex hull of these things, then I obtain again a tetrahedron. Okay, so I think I'm ready now to tell you about Tverberg's theorem. So Tverberg theorem has this philosophy behind about Ramsey type theorem in the following way. So what this theorem says is that if you give me a big enough family of points in d-dimensional Euclidean space, so if you give me a big bunch of points, big enough, then I should be able to partition these color classes into M color classes, these points are into M color classes, such that the convex hull of these convex hulls have a non-empty intersection. This is a special case of Radon's theorem. So let me start with explaining a little bit what Radon's theorem says. So Radon's in the plane, so here we have dimension t equal to, says that if you give me 4 points, and it doesn't matter how you arrange these points, I should be able to partition them in 2 colors such that the intersection of these 2 convex hulls have a point in common. So for instance, here, suppose that Patrick gave me these 4 points. So I'm gonna color the outside points in red, and I'm gonna leave the inside color in gray. So if I take the convex hull of the reds and take the vertex inside, these 2 convex sets are going to intersect precisely in the gray color, and I'm going to have a point in common in these 2 colors. So if I change that and talk about this in terms of nerves, then my nerve is going to be just this simplex, which is a segment over here. But if you change your mind, and you give me, instead of the previous 4 points, you give me this other possibility, then I can also color these 2 points in red and the other ones in gray. And as you can see, if you take the convex hull of the reds and the convex hull of the grays, this is a point in common to the 2 convex sets. So again, I have a point that is common to both of them. And so this is what Radon tells me. And in other words, what I obtain is, as a nerve, is again an interval, or as a easy simplex. Okay, so Radon it was extended by Tverberg in 1966, and what he says is that instead of just having 2 colors, you can do this with any set of colors. So M is going to be my set of colors, and D is the dimension. So if you give me M equal 3 and D equal 4, what Tverberg says is that if you give me this amount of points, doesn't matter how they are arranged, as long as you give me at least those number of points, then I should be able to partition them in color classes in such a way that the convex hull of all these color classes have a point in common. So in the case M equal 3 and D is equal 2, if you just do the numbers, then it tells me that 7 points are enough. So in here, I get 7 points, and I can color them like that. And then if you are following me, then you right away notice that this is a bad coloration, right? Because they have no point in common. So that's not what Tverberg says. So of course, that doesn't mean that any coloration will work. That means that there exists a coloration that works. So in here, I should do this. This is much better. And then once I do that, there is a point in common to all these color classes. And well, what Tverberg says is then I have a point in common. And if I talk about this in terms of nerves, then I have a simplex, okay? An D-1 simplex. Once you obtain a partition that works, that's called Tverberg partition. I should mention here that this theorem is sharp in the sense that if you give me less points than the ones that Tverberg says, then you may not get a partition, a Tverberg partition. For instance, if you arrange the points like these ones on the plane, then it may be good for you if you try to color them with 3 colors, and you will notice pretty fast that doesn't matter how you color them and how much you try, you're never gonna get a point in common to the 3 color classes of the convex hull of the 3 color classes. All right, I hope Tverberg it's clear. I hope Tverberg it's now in, we all understand what Tverberg says. Okay, before I continue, I should mention then, of course, that I can then restate Tverberg's theorem in the following way using nerves, just what I've been telling you. So Tverberg theorem says that if you give me this amount of elements in my points, set of points, with m color classes, then if I should always be able to color them so that the nerve of that partition is an m-1 simplex. Okay, very good. So I should mention here that is a very open conjecture still about its very famous one known Sierksma conjecture, and says that there is not only one Tverberg partition when you give me this amount of points, but m-1 factorial to the d Tverberg partitions. So that's an interesting conjecture that may be attractive to you. Okay, so let me now tell you what Tverberg type of theorems we're interested in. Okay, so now instead of having the simplex, imagine that you give me any simplicial complex that you wish. And the question is now, okay, if you give me sufficiently many points in the d-dimensional Euclidean space, can I find a way of partition them such that the nerve of that partition gives me the simplicial complex you hand me at the beginning? If that happens, then it should exist a constant, right? That's the minimum number of points that allow me to do that. So this is the type of questions that we are interested in. Okay, so we start working with Jesus and Tommy and Dominic in around the 2019, and we find several Tverberg type of theorems in this sense. So we begin talking about trees. Instead of having the simplex, just say you give me a tree, your favorite tree. Is there a way of having enough number of points so we can guarantee that there is always a partition that yields this? So for example, if you give me the points in convex position, then there is a way of codifying these vertices such that you obtain always that as a partition.
Can I ask a question?
Sure.
Sorry, if you mean sufficiently many points in RD, are you asking about one specific point sets where you can do this, or do you want for every point set of
every point configuration? That's a good question, Patrick, because if you just give me a specific one, then perhaps you can say really quickly computationally, yes, this has or not, this doesn't have. But this should work for any configuration of points. So as you can see, once you have, say, you give me configurations of 4 points, that's easy. There are only 2 configurations in general position, only 2 configurations. If you're telling me, okay, 5 points, then I guess there are 16 if I recall correctly. But once you start increasing the number of points, this becomes absolutely crazy and very difficult to manage. So thank you, Patrick.
You're assuming general position for these points, or?
Yes, because
Okay.
if not, then things get a bit easier general, because then you're low in the dimension,
Yeah.
say like that. So yes, general position is usually the most general question.
Okay, thanks.
So for this theorem, we note, if you are familiar with these Ramsey type problems, just notice here that the minimum number we are getting is Ramsey type of numbers, which is a huge number of points. Okay, so as you can see here, this is not sharp at all, but we use, as I explained a little further away, we use some theorems like that guarantee some points in convex position, and there is where I do my partition. Okay, so let me continue over here. So we know that trees work. We know that cycles work. And the bound here is much better because we just organize the points on the plane. Well, here it's in every dimension, but the idea is similar. We partition the space in branches or cones, and then separate and do the coloration like that. So that's why this is much better bound. We also prove that, in particular, when the tree is a caterpillar, then we gave this nice sharp bound. So we know that with this amount of points, you can always guarantee the way of partition them. And we try computationally to find sharp bounds. We know that for the star tree, just you have a vertex and then it's only edges coming out of it. Then we found a sharp bound. But we know that just simple path of length 4, we know that 9 is sharp. Here is a configuration of points, of 8 points that has that not allow P4 as a path of length 4 as a nerve. And we did the same thing with cycle of length 4. And we know that our bounds are between 11 and 13. The 11 we got it also with computational, but that's as far as you can go because already 11 points, it's more than like 15 million points of, it's crazy. So computationally we obtained this bound, and 14 we did it with our methods. So we know the truth is between 11 and 13. Okay, so now let me change the topics. So if you already have sleep, then you can wake up again, and let me change the topic completely. So now I'm going to tell you about words and graphs, okay? So if you give me a graph, I want to be able to find a word that represents this graph in the following sense. So if I have an edge, xy is an edge, if and only if I have an alternating subword of length d plus 2. You will see where the d comes from later on. But so far, for instance, if you give me an edge, then what word would represent this edge? Well, the word AB, AD, AB, AB, okay? This is an alternating word of length 4. So then I will say that this word, this graph G, which is just a single edge, 2 represents my graph G. Now, if you give me the complete graph with 4 vertices, then you may notice here that this word 2 represents as well this complete graph. Notice that I have A, B as a word, so that means that this edge is there. If I want to have this edge AC, then I have AC, AC as well. If I change that and I want to avoid having these two edges, then I have to change my word because I don't want AC, AC to be an alternating subword of this word. So notice here that I change AC and then CA to avoid alternation, okay? So this word now represents this different graph than the one. Let me give you another slightly more interesting graph. So say I have a graph that looks like this. How do I find the word that represents? So this is the word. Again, look at any edge you wish. Say, for instance, 1, 4, 1, 4, 1, 4. So I have an alternating subword that gets together 1 and 4. And that's of length 4, so it's 2 representing. Everything has to be of length 4 if I want this to be 2 represented, okay? So I hope it's clear enough what means that a word D represents a specific graph. If I have words like this, I don't need, I should point this out, that I don't need to have a subword precisely of length 4. I mean, I can have repetitions of one element. So like here, 6, 6, 6, it's repeated several, but as long as I have 1, 6, 1, 6 in my word, then I'm okay. There is an interesting book called Words and Graphs, like just like here, that talks about all these type of words. But in that word, they don't use the repetition. So they have to have precise subwords of this length and no more. And of course, if you do that, then the number of graphs that you can do with this, it's much less. So we proved last year that every graph is D representable for some D, no matter how your graph looks like. So the hard question is how to find the minimum D, because if you can manage to find a D that is very large, but the hard question here is how do you find this minimum D, okay? All right. We look at all possible graphs up to 9 vertices, and all of them are 2 representable, except these 3. So this means that there is no word that have subwords of length 4 that could be expressing these 3 type of graphs, okay? So this, in other words, these particular 3 graphs needs more than 4 alternating words to be represented. Okay. But let me tell you what nice families we know. We know that circle graphs are 2 representable, and that's very easy to see. Perhaps you can convince yourself right away. Circle graphs are those ones that are obtained by, if you have a circle, and then you have placed on the circle all the polygons that are with vertices on your circle. So like this one's over here. And then you place 1 vertex for each, and then you do the intersection graph of that. So these graphs are 2 representable, and the words are very easy because you can say red, green, red, gray, blue, red, etc. And that will precisely give the partition that represents this graph. In particular, this one is a representation graph of this one over here. Okay. Another very nice family that we obtain are bipartite graphs. And we know that these bipartite graphs are D word representable. And the D that we are obtaining is slightly bigger than one of the smallest partition on the bipartition. So in this particular example, for instance, we have this. Furthermore, this theorem not only says that what's the D, that D represents this word, we find an algorithm that gives us the explicit word that codifying this bipartite graph in particular. Okay, so I hope this is clear so far. Okay, my third part of my talk. Now I'm going to put things together. Okay, so now I'll join Tverberg together with words. Okay, how? So I said to you that we were interested on solving these following Tverberg type of questions. If you give me a simplicial complex with n vertices, then I was interested in finding if I have sufficiently many points in the d-dimensional Euclidean space, can I partition them in such a way that the nerve is precisely the simplicial complex you hand me over? Okay, I'll do this one step at a time. And instead of asking for every simplicial complex, I'm going to start with a graph. So suppose, again, Patrick hand me his favorite graph, and he say, okay, Deborah, could you ensure me that this graph is a way that if I give you sufficiently many points in RD, or is there a dimension, first of all, that I can, and that I can give you enough points, then you can guarantee that if there is a way of partition them so that the nerve is a precise graph that you hand me over. Okay, so say this is a favorite Patrick's graph, and then the answer is going to be yes. I'll write down the word that represents that graph. And as I convinced you already, I hope, this graph was two representing this with this word. This word with is two representing this graph, sorry. And now what? Okay. I'll need an important ingredient here, and I'm gonna tell you about Erdos-Sekeres. Okay, Erdos-Sekeres is a beautiful, very well-known theorem, so I'm not gonna talk about that, but let me just remind you what it says. So it says that if you give me sufficiently large set of points, again, this is a Ramsey type of theorem, okay? Then I always should be able to find some of them that are in convex position. How many? Well, depending on how many do you want, how many points I should ask. Okay, so we know that if I'm looking for 3 of them in convex position, then 3 are enough. If you need 4 points in convex position, then 5 points are enough. That's Esther claim. And then if you need 5, 9 are enough, etc. Okay. So, but I'm looking for points in convex position, but in the plane is easy because convex position means that are combinatorially speaking points on a circle. But if you tell me you want to do that in D dimension, then convex position will mean that you are handing me over the vertices of a polytope. And there are lots of possible polytopes that you may give me. So we are going to use this nice version of Erdos-Sekeres in dimension. And that's done by Grumban and Cordoville and Duchet. That says, okay, no worries. If you give me enough points in RD, then I should be able to find there points in convex position, but not only that, I should be able to give you points in the cyclic D polytope. Now, for those of you that don't recall what a cyclic D polytope is, it's just a combinatorially speaking, is the vertices could be place, the vertices have coordinates of the form t, t squared, t cubed, t, etc., up to t to the n. So that's very manageable and easy to see. So let me go back to my question. So here we have the word of my graph, and then I'm going to use Erdos-Shekeres, and Erdos-Shekeres says, okay, my points are, I can give you a graph that is combinatorially equivalent of a cyclic polytope. Therefore, I have a partition that looks like this, combinatorially speaking, okay? Then what I'll do is, okay, then I'm going to take, how many words did I need to codify this word? Okay, here I have this many points, okay? So what I'll do is I'm just going to label the points on my cyclic polytope precisely with the codification that my graph, my word gives me. So in this case, 1, 4, 2, 1, 3, 2, 4, 5, 3, 1, 5, etc. Okay, once I do that, then I'm going to take the convex hall of my classes. So I have the 1s, the 4, 2, and then I right away notice that I have obtained my graph as a nerve of this partition. We use very heavily theorem of Merlin Breen, where she studied the primitive Radon partitions. So basically, we use her theorem to show that with this codification, you don't obtain more intersections than the ones you need, and not less either. Okay, once we have that, remember that I'm using Erdos-Shekeres, and Erdos-Shekeres guarantee the existence of these points in convex position, but what should I do with the rest of the points? So remember that there are a bunch of points somewhere here that I needed to guarantee the existence of those ones over here. So the last part of the theorem was to be able to extend this coloration to the rest of the points. So that's usually not always possible. So if you give me a word, you can find the partition on this cyclic polytope. However, not necessarily you're able to extend it. So in this work, we were not we were able to show some examples that are not extendable. Okay, but we proved that every circle graph is to Tverberg. We also proved that every bipartite graph is D Tverberg for some D. And this is, again, I should mention here that this D is not necessarily the best one. Our algorithm gives us a D and gives us a way to represent it. And then we were able to extend it to every dimension. But, but we don't know what's the smallest D where bipartite graphs can be explained. So I don't know if there's a question so far. All right. Okay. This year, some months ago, Florian Frick and AMC Jeff have extended these ideas of words to more simplicial complexes. These simplicial complexes, they call it weakly D Tverberg, and they also showed that they are D colorful representable. So in other words, they extend the number of simplicial complexes that are that could be partitioned as a Tverberg partitions, and they use some of these ideas of words as well. they are not interested much in generalizing into the whole dimension. They just want to find it in the cyclic polytope, let's put it that way. Okay. All right. What else? Well, let me tell you just briefly some other interesting possibilities and possible applications of this thing. So I'll just talk very briefly that we find a new model using random interval graphs that uses these ideas of nerves. So let me tell you about a very classical problem that says, okay, imagine that you, in my times with you buy cereal, sometimes cereal had a little present on the box. And we wanted to collect the whole collections of the cereals, right? So the question is, how many boxes of cereals do I need to buy to guarantee that I have the full collection of presents in the cereal box? In here, you are interested in collecting some stamps. And what's the probability of getting all the collections if I buy N packages of these stamps, no? This is a very classical problem called the coupon collector problem from back of 1708. Euler and Laplace solved this problem by using where the probability is equal on all the samples. Hermann and von Schelling proved it in 1959 when not equal probability was assumed. And lately, Flageolet, Gardy, and Timonier expand this coupon collector problem to other random processes. So let me go back to my original motivation at the beginning. So we know that in my town there are M type of birds, okay? And I have do my research and suppose that every observation give me a sequence of identical distributed random variables. And I do the same process that I've been telling you around. How many observations I need to make to see all the birds on my backyard? Then if you observe, this is precisely the coupon collector problem. And if I try to translate this as in terms of nerves, then I may be asking, what's the probability that the nerve has precisely M vertices? Okay, so in terms of nerves, that's exactly the question I'm asking. Okay, now imagine that I also want to ask, what are the chances that K of the birds that are on my time do not interact? Then in terms of nerves, I'm asking, what's the probability that my nerve has no edges? Okay. Imagine that I'm asking if there is one bird that two birds, that are present at the same time. So in terms of nerves, I'm asking what's the probability that the J is an edge on my nerve. Okay. Now imagine that I'm interested in other type of questions, like what's the chances that one type of bird is present at the same time that K others? Then what I'm asking is, what's the probability that my nerve has a vertex of degree K, right? Okay, then what are the chances that all birds are present at the same time? Then what I'm asking is, what's the probability that my nerve is a complete graph? So we solve these questions and we find a model that answers these questions. The model that we use very basic probabilistic methods, nothing really complicated. So, but we were able to answer these questions. So I'll just gonna hand you over some open questions that may be interesting to you. So again, finding exact values for these Tverberg numbers are interesting not only for tree cycles or a specific bipartite graphs. In general, how to find better chance not only in the dimension but also in the number of points. Also, computational complexity of these questions are interested, and also now we are asking and try to solve some other random models for other dimensions. And I think that's it, Patrick. I can finish now.
All right, thank you very much for the nice talk. Are there any questions? So while people might be thinking, I have a very small one, so you have open problem 1, 2, 3, and 5. Is there an open problem number 4, or is that not related to the talk?
I made a mistake and I repeat question 2, and I just noticed it this morning. So I say, okay, no, I don't want to question 2.
Okay. No, my actual question is also, what is known about number 3? Like, do you have anything? Because, I mean, you did check it on small point sets. Did you just try all possible partitions there?
No. So, well, we can manage up to 11 points.
Yes, but so for a fixed point set of 11 points, how did you check whether C4 was a graph, whether there was a partition that induced C4 on these points?
You mean how do we do it, or
yes?
Can you ask again?
Okay, so if I understand it correctly, you tried it for every point set on, let's say, 10 points.
Right.
You checked whether this, so for every point set, you checked whether this point set has a partition whose nerve is C4.
Right.
Right. So how exactly did you check that?
We did computationally. We try. We use this. Oh my gosh, I'm gonna be in trouble here because I don't remember the numbers, which are very, very important people here. There is a, let me see if I can remember. There is compension of all possible types of order types. Of
so the order type database.
Right.
Yes, I know that.
I forgot the numbers of this. Sorry about that.
It's also in iFolks, and I think did that.
Yes. Yeah. They have the complete set, so we take it from there, and then we analyze all possible configurations and say this has no, and then it's just a program that does.
Yeah, and so on a single point set, you still look at all possible partitions.
Right.
Okay.
Yes. With this last 5 questions, we are doing some more some random coloration, which simplifies things, but it doesn't give us the clear question of the clear answer of that.
Yeah. Okay. Yes.
Okay.
Thanks. Any other questions? That does not seem to be the case. So thank you again for the talk.